Okay, hi, I'm Richard Milson, and I'm going to show you the Quant model, which is Professor Michael Batty's spatial interaction model. This is a collaboration between the Bartlett Center for Advanced Spatial Analysis and the Alan Turing's Urban Analytics. What Quant is it's a gravity model for the whole of the UK. The map here shows it quite effectively. The map shows all 8,436 zones. So for each one of those zones, there's a little arrow on the map that goes from the zone centroid and shows an arrow in the median direction of the flow of people going from home to work. And you can see how it picks out population centres and employment centres, like it picks out London as a big sink of employment. It picks out some of the other cities like Birmingham and Manchester as well. We have census data for 2011 for where people work and where people live, and we use this to construct the flows of people. We also have all of the public transport timetables for the whole of the UK, and we have the road transport network as well, and that is what we use to create the cost function. So from that we can compute how long it takes to get from zone A to zone B for every combination of zones in the model. And this allows us to produce flows of people traveling from home to work on any one of the three modes, which is road, bus, and rail. Now, as you can see, it's a big model. It's for England, Scotland, and Wales. Now, the size makes it a closed system. If we'd just, say, taken a model of London, you'd always be having problems where there are out of zone flows, moving into the zonal model. By having it as big as this, everybody tends to work and live on the same part of the island. So it's a closed system, but it is computationally complex. With 8,436 zones, there are about 71 million possibilities of flow between any zone and any other zone. So there's 71 million floating point values in every one of the 6 matrices that make up the model. Now, the reason for making the model is that it allows us to do scenarios. Quant can do 2 types of scenario. We can either do an employment scenario, as you see here with the Heathrow residential population, or we can do a network scenario, which is high-speed rail too. Employment scenarios, we just increase the number of jobs in the zones. So for the Heathrow, we've increased the number of jobs in line with the government white paper on where they expect increased jobs to be. What you can see with this is that there's a sort of black area just to the left of centre. That is the greenbelt area, which you cannot build on. So what happens with the Heathrow example is that all of the potential new houses are going to have to be built, pushed into the centre of London, because they're pushed in by the greenbelt. Now, with network scenarios, these are a lot more complicated. What we have to do is change the underlying network and then rerun the shortest path algorithm on that network, on a million node network. It is computationally complex and time consuming. But what you see here is the high-speed to rail example. So the top right one is the original example with phase 1 and phase 2 to Manchester and Leeds. The thumbnail on the bottom left is the integrated rail plan, which is the one that the government released back in November. This is a much more complex example. IRP, it involves faster high-speed links, which are built as new links, upgrading existing links, upgrading and building new stations, and interconnectivity with existing metro and existing bus. But when it's modelled, it does look like it's a better plan. And we've got Camcox, which is Cambridge, Milton Keynes, Oxford, another rail scenario. We have motorway speed limits, which is interesting because we take the motorway network up the speed limit to, say, 80 miles an hour, and then see what the effect of that is. Then we have Crossrail, which is another rail scenario, which is about to go live in London, hopefully in the next few months. Now, these are real world scenarios. Where we are at the moment and where we are going into the future, we're creating synthetic scenarios. We're actually computer generating scenarios. So we're starting to wonder, how do the real world scenarios fit in with the whole search space of all possible scenarios. So we've created lots of randomized scenarios as a baseline to compare against, and we're able to do AI search. So what we can do is say minimize for road kilometers driven, which would be, for example, a low carbon scenario. Now, at the moment, we've got about 100,000 employment scenarios and about 10 to 15,000 network scenarios. And we're using the data mining of that to inform the creation of better scenarios in the future. And with that, that's where I'm going to leave it. Thank you.